Hello, everyone. Thank you all so much for joining tonight for our tech talk on design patterns. Erin Allen will be kicking it off. Super excited for this one. I'll pass it over to you, Erin.
Cool. Thank you very much, Jess. Hello, everyone. My name is Erin Allen. I'd like to start by thanking Jeannie and Bracklet for sponsoring this tech talk on design patterns. So today's talk will be all about design patterns. Well, software ones at least. What makes up a design pattern? Design patterns are solutions to commonly occurring problems in software design. Blueprints we can customize to solve reoccurring design problems in code. But remember, we can't just copy and paste. It's not a specific piece of code, but a general concept to solve a problem. Sometimes they are confused with algorithms because they describe solutions to some known problems. Remember though, an algorithm defines a clear set of actions to achieve a goal. A pattern is more of a high-level description of a solution. A good analogy is an algorithm is a cooking recipe with clear steps to achieve a goal. A pattern is a blueprint. You can see what the results and features are, but the exact order is up to you. So why learn design patterns? Well, they are a toolkit of tried and tested solutions. Design patterns are useful because it teaches you how to solve all sorts of problems using principles of object-oriented design. Another reason to learn them is they define a common language that you and your teammates can use to communicate more efficiently. You can say, oh, just use a singleton for that, and everyone will understand the idea behind your suggestion. So now that we know what makes up design patterns and why we should learn them, it's important to know who is behind creating them. So the first person to actually describe the concept of patterns was Christopher Alexander in his book, A Pattern Language, Towns, Buildings, and Construction. Units of this language are patterns. They may describe items such as how high windows should be and how many levels a building should have. But technically, this is for design patterns in general. We, as software developers, care about software design patterns. So let's give a group of 4 individuals some credit. Because one does not simply explain design patterns without introducing the gang of 4. Not that gang of 4. Not that one either. Really close. Really, really close. But there we go, the actual gang of 4 behind software design patterns. However, we could argue the 4 previous groups bettered our lives in their own ways. The 4 gentlemen here, Eric, John, Ralph, and Richard, are otherwise known as the Gang of 4, published the famous book, Design Patterns, Elements of Reusable Object-Oriented Software. The book pictured there on the right. The book featured 23 patterns solving various problems of object-oriented design and became a bestseller very quickly. This inspired many individuals to discover other object-oriented patterns and utilize a pattern approach in other programming fields. So now that we've talked about what design patterns are, why to learn them, and who's behind them, let's actually talk about the patterns themselves. Design patterns differ by complexity, level of detail, scale applicability to the entire system being designed. Let's use a road construction analogy. We could make an intersection safer by either installing some traffic lights, or we can build an entire multi-level interchange with underground passageways for pedestrians. All depends on which tool is needed to get the job done. All patterns can be categorized by their intent or purpose. There are 3 categories. First, the creational patterns, which provide object creation mechanisms that increase flexibility and reuse of existing code. Structural patterns, which explain how to assemble objects and classes into larger structures while keeping these structures flexible and efficient. And then finally, behavioral patterns. These take care of the effective communication between the assignment of responsibilities between objects. To better understand each category, let's look at some examples. So the first off here, we have the factory method. Factory method is a creational design pattern that provides an interface for creating objects in a superclass, but allows subclasses to alter the type of objects that will be created. The factory method allows us to utilize a superclass and also lets us customize the new returned object. So let's say we're going to create a video game. I don't know, Pokemon. In Pokemon, we need different types of Pokemon: grass, fire, water. And the best way to do this is to correlate each type to a class. For each new Pokemon, we would need to make a new instantiation of that class or type. When we start off with 3, it wouldn't be so bad. But when we realize we want more fun with over 15 types, this is where we come into a problem. The amount of code to create objects will gradually increase and will become scattered across the application. If class names are hard-coded and the complexities of managing the code will keep increasing as you add new classes to the application. This is where the factory method comes into play. So for us, I have a code example. So a quick disclaimer, in the essence of time, the coding examples in my presentation have already been built and compiled. I did this so we can focus on the output to showcase the benefit of the design patterns. Go ahead, run. Code here. Load. To run, and there we go. So as we can see, the client ran here, and we have the creator and superclass that were called twice, right? And thanks to our subclasses, our electric type creator and our fire type creator, we were able to create 2 different objects in return using the factory method. So next up is a decorator design pattern. The decorator is a structural design pattern that lets you attach new behaviors to objects by placing these wrappers inside special wrapper objects. Usually when we think about altering an object's behavior, we think about extending a class or inheriting from another class. However, there are some caveats. Number 1, inheritance is static. We can't alter the behavior of an existing object at runtime. We can only replace the whole object with another one that's created from a different subclass. Number 2, subclasses can only have just one parent class. In most languages, inheritance doesn't let a class inherit behaviors of multiple classes at the same time. The decorator pattern allows us to attach additional responsibilities to an object dynamically and extend its functionality. So for example, let's say we want to create an application where we have a file source class, and after we instantiate a new file source object, we want to be able to encrypt and compress the file using 2 separate encryption and compression classes. However, as I mentioned before, one class cannot inherit behaviors of multiple classes. With the decorator design pattern, we can utilize both the encryption and compression classes as wrappers to achieve our desired result, and more importantly, dynamically at runtime. Done. And there we go. So as shown in the output, thanks to the direct decorator method, we're able to change the behavior object at runtime. You saw that. When I ran the code, we're able to change the result. The first example here is just a simple component, our file data source, where we have our write function, we invoke that, and we're just saving a game file. However, the second output, we're able to utilize this encryption decorator and compression decorator to now change the behavior of just our file data source. We're able to now use the write method of both of our decorators to now not only save the game file, but encrypt it and then compress it. So our last example is the memento. Memento is a behavioral design pattern that lets you save and restore the previous state of an object without revealing the details of its implementation. You might be thinking, can we implement a save/undo feature with a design pattern, without a design pattern? Well, we could, but if we are trying to use true object-oriented programming, we would technically be violating encapsulation and exposing internal states of our object. With Memento, we can implement a save/undo feature with our objects violating that encapsulation. We can still capture and externalize an object's internal state so the object can then be restored to the state later. So now say we want to create an amazing open world RPG game, and we want to be nice to our players though, and allow them the ability to save their game, because there might be a scenario where someone messes up and they just want to go back, a couple of levels. In this scenario, the game itself would be considered the object, and we want to keep track of the state or data of the game, as well as keep everything internal to that game object. Another example would be if we wanted to design a text editor application and we want to have the option to undo or return to a previous state. And I'll have our last coding example for us here. Go ahead and run this. While it runs. And there we go. As you can see here, our first line is our initial state. Then we're able to change it three different times. And then after that, we're able to roll it back. And there we go, just like that, we implement the memento pattern, as well as most importantly, keep our objects data encapsulated. So it's dangerous to go alone. Take this, some software engineering advice. Here are some questions to consider when using your newfound power. Is the pattern just a workaround? Usually the need for patterns arises when people choose a programming language or technology that lacks a necessary level of abstraction. Patterns could potentially become a kludge, or in other words, a makeshift, inefficient, inelegant solution that gives the language a much needed super abilities. For example, let's say you want to grab some cookies off the top shelf of your kitchen. You can use a step ladder, which is safe and sturdy, or you can find a box. Both get you cookies, but the box most likely will break after a few uses. The box in this scenario would be the kludge, a quick and dirty fix, but not sustainable or maintainable. Another question to ask, is the pattern an efficient solution? Individuals try to systemize pattern approaches and don't think how the pattern really applies to the project. This creates a dogma of sorts, and developers just want to implement patterns to the letter. This, in turn, might create inefficient solutions. Instead, we, as mid and senior developers, should remember they are just blueprints and we should adapt them to the context of the project. And then finally here, is the pattern use justified? If all you have is a hammer, everything looks like a nail. Once we learn patterns, we want to use them everywhere, but that is not always the best option. Sometimes the simpler code is the best. And so now that we all learned about design patterns and how to implement a few, I think we all can relate to the memes on this picture. And that was my presentation. And thank you very much for listening.
Awesome. Thank you so much, Aaron, for this informative talk on design patterns. Everyone unmute and give Aaron a round of applause.
Yeah, let's go, Aaron.
Hey.
You the man, Aaron.
Awesome. Now, I think we have time for one question. I think, does anyone have a question for Aaron tonight? Okay, no worries. Thank you so much, Aaron. I really appreciate this tech talk. It was super informative, and thank you everyone for joining us tonight. I'll see y'all later.